I want to first to thank this for the opportunity for the international conference on wireless and mobile network for this opportunity. I want to thank you for sure, Mr. Naga, for this handling for this session, and I want to thank Mr. Fabrizio from tomorrow and Mr. Farhi Marir. He was supposed to be the session chair for today. If you would allow me, let me introduce myself if it's in a minute. My name is Mohamed Khalifa. I am a senior engineer at the National Telecom Regulatory Authority in Egypt, which is responsible for the telecommunication regulations in our country. And this research paper is under the supervision of Professor Dr. Hebat-Allah and Professor Mahmoud Abdelaziz for sure. And my research paper is about the separation distance reduction between 5G new radio base station and the satellite earth station at C-band. But first, I will discuss about the objective of my presentation. The objective of my presentation is to get to know the status of the C-band around the world and why there is a need for the 5G new radio why to deploy the 5G in this band. Also, I will discuss how this can coexist with the satellite systems that we are used right now. And I mentioned the satellite system by the fixed satellite service. And I will explain what is mean by fixed satellite service. Also, I will discuss about the methods I proposed and what are. And before I discuss the method, I will mention what are the interference scenarios between the 5G and the satellite. And after I will discuss the method, I will give you the results I get, and finally I will get to the future work that I am supposed to do, and what are the future work, and shall we start with my first presentation? The first slide is about the snapshot of the 5G new radio spectrum. Many countries has assigned the band for the C-band as a potential 5G new radio from 2007, from starting the WRC, the World Radio Communication Conference. And it's the conference that it's putting all the regulation and the recommendation to use the scarce resources of the spectrum, of our spectrum. So from 2007, the issue of C-band arises. In 2015, some parts of the band are harmonized and used as in the LTE, because there was no 5G there. In 2018, China has assigned this band for using so mobile systems in Arab country, in the Arab countries. So as I am from Egypt, so I am related to the Arab countries. In the band, parts of the band from 3/4 to 3.8 were assigned in different Arab countries. And in Egypt right now, we are considering and discussing the band from 3.4 to 3.8 for be assigned for the 5G. Here, if you can see, this is a snapshot of the locations for different countries, from USA, from Canada, from Japan, from India. So this is the licensed and the unlicensed for sure for the band. As you can see in this is what we are talking about. This is our topic in the C-band. After that, I will we finish. After that, we are talking about the FSS system. As you know, the satellite system is important to be used right now, and they're providing many services like broadcasting, right, using in mobile backhaul, like using in maritime, using in the telemedicine. So this is a critical frequency band for the FSS. Because its can reach a distant area rather than the KU band and the KE band. So a feasibility of the study need to be considered. In this slide, we discuss about the interference scenarios and where we are. As you can see, we have here an 8 interference scenario, and we are in this one in the base station that will cause an interference to an Earth station. This is what we are here now in the number 1, and we will discuss what we are doing in this scenario. In the next slide, we will discuss that what are, after we define the interference scenario you are using for, what are the interference mechanisms that we are facing. We are facing 2 issues. If we are in band emission, if there is going to be in the same band, we are facing in band emissions which will affect on the Earth station filtering, and they cause it from non-linear region to and cause it to a non-linearity region, and it will cause it finally to saturation. So this is a problem, but we will not discuss this problem. We will discuss the problems that they are adjacent to each other, and there is an out of band emission from the 5G system to the satellite system, and this is what we are discussing here. In the next slide, after we discuss what we are going to do, the mitigation techniques that people will use to solve this issue. We have here 7 mitigation technique. We have a protection distance, we have a guard band, we have putting filtering at the Earth station. We could make a power control on the base station. We could make site shielding on the Earth station. We could make using the MIMO and making a beam pointing toward towards the Earth station or switch off. I mean the beam of the 5G base station, and we can using an adaptive beamforming. So this is our the mitigation techniques that we are that's already coming to solve this issue, but we are talking about the 2 methods, which are the protection distance and the guard band. These are our 2 issues they are discussing. In the system model that I propose, we here propose the system model for the adjacent bands, and we can see here that the interferences are coming from the 5G base station towards the Earth station, and we will discuss what we are doing in this, and we will figure how this separation distance will be applied, and what are the guard band between these 2 frequency band will be applied. And this is a figure to show you what are the interference coming from. In the next slide, we will spreading the spectrum band we are using. We have here the spectrum band that is assigned for the 5G. Here 3.4 to 3.6, and we are putting a guard band. It's 100 megahertz, and we'll discuss why it's 100 and it will be less than 100. But for now, we will assume that's 100, and this is the band from the satellite Earth station. So after that, we are discussing about the band, and we will going into the parameters and the characteristics for the post system, for the satellite system and for the 5G. For the satellite system, we're proposing the protection criteria, and this is from the recommendation from the ITUR, and this we are going to this recommendation for the 6% increase in the noise temperature from the system. So this percentage will correspond to an I/N interference over noise ratio value, which will be -12. So this is the protection criteria we are using. These are the Earth station of access gain that we are using in our model, and this is the equation for it, and also the maximum interference that the Earth station can handle by using this equation. It's also from the ITUR recommendation. And the values we are proposing the transponder bandwidth 36 megahertz. This is the band we discussed before, the band for the downlink frequencies for the satellite system, the reference pattern, the diameter for the antenna, and the noise temperature. This is the noise temperature I used according to the ITUR recommendation also, and this is I/N value, which is 6%, and it will reflect to the -12.2 dB, and also the Selmer equivalent factor, it will be considered as 0 dB as it's a digital system. For the 5G base station or the new radio base station, we are having 3 types of base station according to the 3GPP standards, we are discussing only the wide area base station, and we are not taking the medium range or the local range, because the medium range will cause a lower interference impact than the wide range, because it will be a micro cell and not a not a big cell. So, and also for the picocell, it will have a lower interference impact, as the picocell can be used in the indoors. So it will be much more interference impact because of the penetration walls and buildings and others. So we will focus on the wide area base station. To continue the characteristics from the 3GPP standard, we have the unwanted emission, and which is the emission from the band from the 5G to the adjacent band of the satellite service. And it's in here in this recommendation we are discussing the spurious emission, to be exact, the spurious emissions from the 5G base station. And for that, it will take from the recommendation from the 3GPP, it will be to an offset of 40 megahertz from the band. So if, for example, if we have a 100 megahertz band, so we must taking into consideration a 40 megahertz guard band, and started from this 40 megahertz guard band. So if we want to deploy a system, let's say an 100 megahertz band plus 40 plus 1 megahertz for safety, so we start at 141 megahertz. After that, if you can see, this is the figure from the offset. As you can see in this table, this is the 3GPP standard for the out band emission. I draw it through MATLAB, and this is the emission. And you can see here at after 41 gigahertz here, this is the value from the GB standard it will follow, and it will be negative 26 dB. So this is for the safety of the base of the FSS Earth station to work and not causing any coexistence interference issue. So this is the spectrum mask from the 3GPP standard. After that, we using the interference from the IMT base station to the Earth station, and also the propagation model we use a free space loss propagation model, and this is a propagation model we are going to use in the 3.5 gigahertz system, and it will use it to determine what are the distance, the separation distance. If you can see here, this is the D, so we will determine what are the best distance that can be fit in order to coexist with the two systems. And these are the parameters for, as for the FSS, this is the parameter for the 5G also. The bandwidths are 100 megahertz, the maximum output power is 50 dBm, the antenna gain, and the 3GPP standard we are following, and it's under the release 17 at its most recent release, and the frequency band you are using. So right now the deployment will be as this, from 3.5 to 3.6, or 3.559 to 3.659. So this is the two deployment. So as you can see, if we discussed before that the offset will be 40, so we'll start the guard band at 41, or we can start the band as the standard model at 1 megahertz. So if you can see here from 41 megahertz until 100 megahertz, there is no difference too. So we can start from 41, or you can start as 100 megahertz. So as it's convenient to the operators. And we have here the transponder 36 megahertz. This is the transponder, and we will do the analysis based on this figure. This is the flow chart of what procedures we are using and what to get the calculation. We first take the I over N protection distance, protection criteria, and then we calculated the maximum interference that get from the Earth station. Then we calculate the unwanted emission ARP for each transponder, that we have one transponder. Then we calculate the minimum pass loss. And in the other section from the 5G, we calculate the free space pass loss, and we are comparing the minimum pass loss that get out from this path with the pass loss from this equation from the propagation model used for the 3.5 gigahertz, and we get the calculation D, and finally we get the results of the D. If you can see, this is the results we are get. So as you can see here, at 41 gigahertz, 100 megahertz, we can put we can make a separation distance between the two stations, the 5G and the Earth station, around 300 meter. So as you can see, as long as the elevation angle or increases, you can see here the separation distance, the D decreases. And as long as the guard band U decreases, the protection distance is increased. So as you can see here, as long as you increase the guard band, the protection increases. As long as you increase the elevation angle and you go with the angle from, this is the elevation angle, if you can, I will get you. This is the elevation angle. So as long as you get up with elevation angle, the distance will decreases. So as you can see here in the, if you can see here in the guard band from 100 megahertz to 40 megahertz, you can see that this is the protection distance 26 kilometers. So this is my conclusion, that in order to put the station, you can do it as a 300 meter and doing a guard band from 41 to 100 megahertz at 48 elevation angle. But what are the future work? The future work is here that we're discussed. For sure, I prepare a second paper and I will publish it soon. Is how we can going from the 26, as you can see here, from the 26 kilometer to 30 kilometer by changing the spectrum mask. So as you can see here, I changes the spectrum mask to start not from 40 megahertz offset, but start from 30. For sure, this will make an when you implement when you implement the 5G base station, it will face an issue with the RF components, and this is what we are going for future work on how we can start with 30 gigahertz instead of 40 to make it the separation distance instead of 26 kilometer to 300 meter. So this is our future work, and for sure right now I am preparing the second paper, and for second paper I will propose a new method to solve this issue. Thank you for attention, and